Welcome to our discussion on LeetCode problem number 698, partition to k equals some subsets. In this problem, we'll explore how to determine if an array can be divided into k subsets with equal sums. It's a fascinating challenge that combines mathematical reasoning and algorithmic problem solving. Let's dive in. In this problem, you are given an integer array called nums and a value k. The goal is to determine if it's possible to divide the array into k non-empty subsets where the sum of the elements in each subset is exactly the same. For the input, the array nums can have a length between 1 and 16, with each element being a positive integer up to 10,000. The value of k will always be at least 1 and at most the length of the array. The output is a Boolean value, true if the array can be partitioned into k subsets with equal sums, and false otherwise. Let's look at an example to better understand the problem. Consider the first example where nums is 4, 3, 2, 3, 5, 2, 1, and k is 4. In this case, the output is true. The array can be partitioned into 4 subsets, 5, 1, 4, 2, 3, and 2, 3. Notice that each subset has a sum of 5, which satisfies the condition. Now, for the second example, we have nums as 1, 2, 3, 4, and k is 3. Here, the output is false because it's not possible to divide the array into 3 subsets where every subset has the same sum. So, while the first example works, the second does not, highlighting the importance of how the array is structured and the value of k. In the second example, the reason it fails is that the total sum of nums cannot be evenly divided into 3 equal parts. This brings us to the constraints and edge cases. First, the array length is always between 1 and 16, and each element is a positive integer between 1 and 10,000. The value of k is always at least 1 and at most the length of the array. Key edge cases include scenarios where k equals the length of nums, meaning each subset must contain exactly one element, or when k equals 1, requiring the entire array to form one subset. If the total sum of nums isn't divisible by k, we can immediately return false. Similarly, if any single element in nums is larger than the target subset sum, it's impossible to form valid subsets. For very small arrays, the solution should be efficient enough to handle them without unnecessary computation. These constraints and edge cases help guide us as we approach solving this problem. To solve the problem of partitioning an array into k subsets with equal sums, we need a strategy that balances feasibility and efficiency. One approach we considered is the brute force method. Here, the idea is to generate every possible way to divide the array into k subsets and verify if any of these partitions result in subsets with equal sums. While this method is straightforward, it is computationally expensive because generating all partitions has an exponential time complexity of approximately k to the power of n, where n is the size of the array. This makes it impractical for larger inputs. Another approach is backtracking with pruning. With this method, instead of exhaustively generating all partitions, we build subsets incrementally and backtrack whenever we encounter an invalid configuration. The key insight here is to ensure that the sum of any subset does not exceed the target sum, calculated as the total sum of the array divided by k. Additionally, if the total sum of the array is not divisible by k, we can immediately conclude that the partition is impossible. Sorting the array in descending order before applying backtracking further optimizes the process by reducing unnecessary recursive calls when larger elements are considered first. Backtracking with pruning offers significant improvements over brute force, as it reduces the search space considerably. Although its time complexity is still exponential in the worst case, the pruning step ensures that we skip over invalid configurations early, making it much faster for moderate input sizes. However, this method does require careful bookkeeping to track the sums of subsets as we assign elements to them, which can be complex for highly constrained inputs. Another approach we explored is dynamic programming with bitmasking. In this method, we use a bitmask to represent which elements of the array have already been used, and a DP table tracks whether a specific subset sum can be formed with a given combination of elements. This approach is more efficient than backtracking in some cases, with a time complexity of n*2 to the power of n, where n is the size of the array. However, it comes with a trade-off. The memory requirement for the DP table can be significant, especially for larger arrays. While it is faster for smaller values of k, the memory demands limit its practicality for large inputs. Among the approaches considered, backtracking with pruning emerges as the most balanced solution. It combines conceptual simplicity, reasonable implementation complexity, and manageable computational efficiency. Unlike dynamic programming, it avoids the heavy memory usage associated with maintaining a large DP table. At the same time, it is far more practical than brute force, which is infeasible for all but the smallest inputs. To optimize the backtracking process, we sort the array in descending order so that larger elements are placed first. This strategy minimizes the likelihood of running into invalid configurations early in the recursion tree. Additionally, once a subset reaches the target sum, we can skip further recursive calls for that subset, saving valuable computation time. Despite its advantages, backtracking with pruning can still be slow for edge cases with many valid configurations, especially when the input size grows large. In summary, while brute force is too slow and dynamic programming can be memory intensive, backtracking with pruning provides the best overall trade-off between speed, memory usage, and ease of implementation for this problem. The problem asks us to determine whether an array can be partitioned into exactly k subsets, where each subset has the same sum. This is a combinatorial problem that requires carefully exploring various subsets while ensuring all constraints are satisfied. To approach this systematically, we use a technique called backtracking with state compression, which is well suited for problems that involve recursive exploration and optimization. First, we pre-process the input. The target sum for each subset is calculated by dividing the total sum of the array by k. If this division is not exact, meaning the total sum is not divisible by k, we can immediately return false because equal partitioning is impossible. Next, we sort the array in descending order. Sorting helps by placing larger numbers earlier, which can quickly invalidate configurations that exceed the target and reduce unnecessary recursion. If any single number in the array exceeds the target, we can also return false immediately, as no valid subset can include such a number. The next step is implementing recursive backtracking to assign numbers to subsets. We represent the current state using a list of buckets, where each bucket tracks the sum of one subset. At each step, we consider the current number from the array and attempt to place it into one of the buckets. The base case of our recursion occurs when all numbers have been processed, and every bucket exactly equals the target sum. If this condition is met, we return true. For the recursive case, we try placing the current number into each bucket. If adding the number to a bucket does not exceed the target, we temporarily update the bucket sum and proceed to the next number. After exploring this option, we backtrack by removing the number from the bucket to restore the previous state. Pruning plays a key role in improving efficiency. By skipping buckets that are identical to previously considered ones, we avoid redundant work. Additionally, if a bucket is empty but capable of holding the current number, we can short-circuit further attempts with other buckets, as the configuration would ultimately be redundant. Now, let's look at the implementation of the algorithm. We define a function called canPartition k subsets, which begins by calculating the total sum of the array. If this value is not divisible by k, we immediately return false. Next, we calculate the target sum for each subset and sort the array in descending order. Sorting ensures that larger numbers are processed first, helping to prune invalid configurations early. If the largest number in the array exceeds the target, partitioning is also impossible, so we return false. To track the sum of each subset, we initialize a bucket's array of size k, where each bucket starts at 0. The recursive backtrack function is then defined. It processes each number in the array, attempting to place it into one of the buckets. If all numbers are assigned successfully and all buckets match the target sum, we return true. Otherwise, we explore alternative configurations by backtracking. The backtracking function includes additional optimizations to improve efficiency. Specifically, pruning is applied to avoid redundant configurations. For example, if a bucket remains empty after trying to place the current number, there's no need to attempt other buckets in this iteration, as the result would be the same. This ensures that unnecessary recursive calls are avoided. Finally, the backtrack function returns false if no valid configuration is found after exploring all options. By incorporating these pruning techniques alongside recursive exploration, the algorithm effectively manages the complexity of the problem. With these elements in place, we return the result of the backtrack function starting from the first number in the array. To summarize the data structures and complexity of the algorithm, we use a buckets array to track the sum of elements in each subset, which allows for quick validation of whether adding a number to a subset is valid. The recursive stack handles the backtracking process, ensuring that all configurations are explored systematically. In terms of time complexity, the worst-case scenario involves exploring all possible subsets, which results in O, k to the power of n, where n is the size of the array. However, optimizations like sorting and pruning significantly reduce the number of subsets that need to be explored in practice. The space complexity is O, k plus n, accounting for the buckets array and the recursion depth. For edge cases, the algorithm handles scenarios like when a single element exceeds the target, when k is greater than the array size, or when k is equal to 1, which always results in a valid partition. Zeros in the array are naturally handled without requiring special treatment. Sorting the array in descending order ensures that larger numbers are placed first, helping to minimize invalid configurations early in the recursion process. This simple step greatly reduces the search space and improves overall efficiency. Additionally, pruning redundant bucket configurations further optimizes the algorithm, particularly for larger inputs, by eliminating unnecessary recursive calls. Together, these techniques strike a balance between correctness and performance, allowing the algorithm to handle complex inputs effectively. The combination of backtracking, state compression, and targeted optimizations ensures that the solution is both robust and efficient, making it well-suited for solving this challenging partitioning problem. Here, we start defining the canPartition k-subsets function within the solution class. The first step is to calculate the total sum of the input list, nums. If this total sum is not divisible by k, then it's impossible to partition the array into k-subsets with equal sums, so we return false. Next, we determine the target sum for each subset by dividing the total sum by k. Sorting the numbers in descending order helps optimize the backtracking process by attempting to place the largest numbers first. Additionally, if the largest number in the array exceeds the target sum, it's immediately clear that partitioning is not possible, so we return false. After that, we initialize an array, buckets, to keep track of the sums of the k subsets, all starting at 0. Finally, we define a helper function, backtrack, which will handle the recursive backtracking logic. The base case checks if all numbers have been placed, and if so, verifies whether each bucket has reached the target sum. Within the backtrack function, we iterate through each bucket to try placing the current number, nums, index. If adding this number to a bucket does not exceed the target sum, we temporarily place it in the bucket and proceed to the next index by calling backtrack recursively. If the recursive call returns true, it means we've found a valid partition, so we return true. If not, we backtrack by removing the number from the bucket, effectively undoing the last action. For optimization, if a bucket is empty and the current number doesn't fit, there's no point in trying other empty buckets, so we break the loop early. If no valid configuration is found after trying all buckets, the function returns false. Finally, the initial call to backtrack, 0, is made, starting the recursive process to determine if the array can be partitioned into k equals some subsets. Here, we begin by importing the necessary libraries and defining our solution class. The key method, canPartition k-subsets, takes an array of integers, nums, and an integer k, which represents the number of subsets we want to divide the array into. The first step is to calculate the total sum of the elements in nums. If this total sum isn't divisible by k, it's immediately impossible to partition the array into k equals some subsets, so we return false. Next, we calculate the target sum for each subset by dividing the total sum by k. To optimize our logic, we sort the nums array, which helps in placing the largest numbers first during the backtracking process. Additionally, there's an early exit condition. If the largest number in the array exceeds the target sum, we know partitioning is impossible, so we return false. Finally, we initialize an array of buckets to keep track of the sums of our k subsets, and we call the helper function backtrack to handle the recursive logic for partitioning. The backtrack function is a private helper method that implements the recursive logic for partitioning the array. It first checks if we've placed all the numbers by verifying if the index is less than 0. If so, the method ensures that all buckets contain exactly the target sum. If any bucket doesn't, it returns false. Otherwise, it confirms a valid partition and returns true. The main loop iterates through each bucket, attempting to place the current number into a bucket if doing so doesn't exceed the target sum. If the number fits, it's added to the bucket, and the recursion proceeds to the next number by calling backtrack with a decrement index. If the recursive call indicates success, we return true. Otherwise, we backtrack by removing the number from the bucket, effectively undoing the current placement. To optimize further, if a bucket is empty after trying to place a number, we skip trying other empty buckets since it would lead to redundant computations. If none of the buckets can accommodate the current number without exceeding the target sum, the method ultimately returns false, indicating that partitioning is not possible for the current configuration. This structure ensures that the function explores all valid placements of numbers across the buckets while efficiently pruning invalid paths through the use of early exits and optimizations. By leveraging recursion and backtracking, this implementation systematically attempts to find a solution, ensuring correctness while minimizing unnecessary computations. In this example, we aim to partition the array nums, which is 4, 3, 2, 3, 5, 2, 1, into 4 subsets such that each subset has an equal sum. First, we calculate the total sum of the array, which is 20. Since we have 4 subsets, the target sum for each subset is 20 divided by 4, which equals 5. To simplify our process, we start by sorting the array in descending order, resulting in 5, 4, 3, 3, 2, 2, 1. We then initialize an array of buckets to keep track of the sums of our subsets, starting with 0, 0, 0, 0. Using a backtracking approach, we attempt to place each number in the array into one of the buckets. For the first iteration, we take the largest number, which is 5, and place it into the first bucket. This gives us updated buckets 5, 0, 0, 0. Next, we proceed to the second number, which is 4. Since the first bucket already contains 5, we try placing 4 into the second bucket. This results in the buckets being updated to 5, 4, 0, 0. For the third number, 3, we try placing it into the third bucket, as it fits within the target sum. The buckets now become 5, 4, 3, 0. For the next 3, we place it into the fourth bucket, updating the buckets to 5, 4, 3, 3. Now, we move to the number 2. Since adding 2 to the second bucket still keeps the sum within the target of 5, we place it there. This updates the buckets to 5, 5, 3, 3. Continuing with the next number, which is another 2, we find that it can fit into the third bucket without exceeding the target sum. This updates the buckets to 5, 5, 5, 3. Finally, for the last number, 1, we place it into the fourth bucket, as adding it keeps the total at 5. The buckets are now 5, 5, 5, 5, and all buckets match the target sum. Since we've successfully distributed all numbers into the buckets, we return true, indicating that partitioning is possible. In this next example, the array nums is 1, 2, 3, 4, and we're tasked with partitioning it into 3 subsets. The total sum of the array is 10, and dividing this by 3 gives us approximately 3.33, which is not an integer. Since the target sum for each subset must be an integer, it is immediately clear that partitioning the array into equal sum subsets is impossible. Therefore, we return false. For the final example, the array nums is 2, 2, 2, 2, 3, 4, and we are asked to partition it into 4 subsets. First, we compute the total sum of the array, which is 15. Dividing 15 by 4 results in 3.75, which is not an integer. Because the total sum is not divisible by the number of subsets, it is impossible to create subsets with equal sums. As a result, we return false. To analyze the time complexity of the backtracking solution, we need to consider the operations performed at each stage of the algorithm. First, the input array nums is sorted in descending order, which is an n log n operation. Sorting ensures that larger numbers are handled first, potentially pruning invalid states earlier. Then, the backtracking process begins. At each recursive step, the algorithm attempts to place the current number into one of the k buckets. For each bucket, we check if adding the number exceeds the target sum. This means that in the worst case, we explore all possible ways to distribute the n numbers into k buckets, which greatly influences our time complexity. Now, let's formalize the upper bound for this process. The total number of states we might explore is bound by k(n), because each of the n numbers can theoretically be placed in any of the k buckets. At each recursive call, we iterate through these k buckets, which adds k work per state. This gives us an upper bound of k(n plus 1). However, optimizations such as skipping empty buckets and sorting the array in descending order help reduce the number of states actually explored. Sorting ensures that larger numbers are considered first, enabling the algorithm to reject invalid states earlier. Even with these optimizations, the asymptotic upper bound remains k(n plus 1). When we combine the sorting step, which is n log n, with the backtracking, the overall time complexity is dominated by the exponential component, making it k(n plus 1). Turning to space complexity, we consider the memory requirements of the algorithm. The first major contributor is the recursive call stack. Since each recursive call processes one element of nums, the maximum depth of recursion is n, resulting in n space used for the stack. The second contributor is the buckets array, which tracks the current sum in each of the k buckets. This array uses k space. Finally, the input array nums is sorted in place, so no additional memory is required for sorting. If we account for the input array itself, it adds n to the memory footprint. Combining these, the overall space complexity is n for the stack plus k for the buckets, giving us n plus k. Let's now discuss how the algorithm performs in different scenarios. In the best-case scenario, pruning occurs early, either because a number exceeds the target sum or because a valid partition is found quickly. Here, the time complexity is dominated by the sorting step, which is n log n. In the average case, the algorithm benefits from optimizations like pruning and sorting but still explores a substantial subset of states, resulting in a time complexity between n log n and k(n plus 1). The worst-case scenario involves exploring all possible placements of the n numbers into k buckets, leading to the full k(n plus 1) complexity. Comparing this to a brute force approach, which generates all possible partitions, the optimized backtracking is significantly more efficient. Brute force has a complexity of k to the power of n*n, which is far worse than the provided solution. The optimizations in our approach, like sorting and skipping redundant checks, reduce the number of explored states and make the algorithm much faster in practice. Finally, let's solidify our understanding of the time complexity with a mathematical perspective. In the worst case, each of the n numbers can be placed into any of the k buckets, resulting in k to the power of n possible states. For each state, the algorithm performs k work to iterate over the buckets, leading to a total complexity of k(n plus 1). The sorting step, which requires n log n, is insignificant compared to the exponential growth of k(n plus 1 as n increases. This confirms that the overall time complexity is k(n plus 1). For space complexity, the recursive call stack uses n, and the buckets array uses k, giving us a total space complexity of n plus k. This completes our analysis of the algorithm's efficiency. When solving this problem, there are some common pitfalls to watch out for. First, not handling edge cases properly can lead to wasted effort. For example, if the sum of the array isn't divisible by k, it's impossible to partition it into k equal subsets. This is a simple check that should be done upfront to avoid unnecessary computations. Another mistake is ignoring the importance of sorting. Sorting the numbers in descending order helps prioritize larger numbers first, which can reduce the number of recursive calls and make the backtracking process more efficient. Additionally, using mutable state inefficiently can cause subtle bugs. For instance, if you're modifying a shared list to track subset sums without properly backtracking, it can corrupt your state and lead to incorrect results. A better approach is to rely on local variables or ensure that the state is restored after each recursive step. Another common mistake is failing to prune the search space effectively. If you don't skip duplicate numbers or subsets that already match the target sum, you end up performing redundant computations, significantly increasing the time complexity. Pruning techniques, like skipping subsets that are already valid, help eliminate unnecessary work and make the algorithm run faster. Additionally, overcomplicating the problem can be counterproductive. While advanced techniques like dynamic programming might seem appealing, they're not always necessary. For this problem, starting with a simple depth-first search or backtracking approach is usually sufficient. Once you have a basic solution, you can focus on optimizing it incrementally, rather than over-engineering right from the start. For interviews, it's important to approach this problem strategically. At its core, this problem is about subset sum logic combined with partitioning, and interviewers are often evaluating your ability to balance correctness with efficiency. Recognizing patterns can be helpful. This falls into the category of combinatorial optimization problems, similar to knapsack or subset sum. One critical optimization is sorting the array in descending order and prioritizing larger elements during backtracking. This helps you identify invalid configurations early and saves valuable computation time. Don't forget to discuss edge cases during the interview, such as scenarios where k is greater than the number of elements in the array, or where the array contains zeros or negative numbers, even if negatives aren't allowed in this specific problem. Lastly, be prepared to explain the time complexity of your solution clearly. The worst-case complexity is approximately k times 2 to the power of n, due to the exploration of subsets. This problem is closely related to other problems on LeetCode, and understanding these connections can help you build transferable problem-solving skills. For example, LeetCode 4.16, partition equals subset sum, is a simpler version of this problem where k is fixed at 2. Another similar problem is LeetCode 4.73, matchsticks to square, where k is fixed at 4, and there's an additional restriction on the sum. Of course, the problem we're discussing, partition to k equals some subsets, generalizes these. You might also look at the subset sum problem, which focuses on finding a single subset with a target sum rather than partitioning the entire array. Lastly, LeetCode 2542, maximum subsequence score, involves selecting subsets under constraints, although the goal is different. Exploring these related problems can deepen your understanding of subset-based algorithms. There are several alternative approaches to solving this problem, each with its own trade-offs. One option is using bitmasking combined with dynamic programming. This approach represents subsets as bitmasks and uses a DP table to track their feasibility. While it avoids recursion stack overflow, it can be memory-intensive, and the time complexity remains exponential. A greedy approach is another possibility, where numbers are assigned to subsets iteratively to balance the sums. However, greedy methods don't always guarantee correctness for all configurations. Brute force is the most straightforward method, enumerating all possible partitions, but it is impractical for larger inputs due to its extremely high complexity of k raised to n. Finally, heuristic-based optimization combines backtracking with techniques like targeting subsets with the smallest remaining capacity. While this can improve performance in practice, analyzing it theoretically can be more challenging. Each method offers a different balance of efficiency and complexity, so the choice depends on the problem constraints and input size. To wrap up, we covered an elegant solution to the partition to k equals some subsets problem using backtracking and pruning. Remember, these techniques are not only effective but also essential for tackling similar problems. Thank you for watching, and don't forget to like and subscribe for more insights. Keep practicing and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!